Good afternoon, everyone. I'm Zhikang Chen from Tsinghua University. Today, I will present our work ClubHeap, a high-speed and scalable priority queue for programmable packet scheduling on behalf of the authors. This work is based on a popular programmable scheduler abstraction called PIFO. The presentation will answer three questions. First, why are the priority queues crucial for programmable schedulers like PIFO? Second, what are the problems with the existing priority queues? And third, how did we design ClubHeap to address these problems? We start from the significance of priority queues in programmable schedulers like PIFO. PIFO is an abstraction that can implement a wide range of scheduling algorithms. It pointed out that all scheduling algorithms make two basic decisions: in what order packets should be scheduled and when packets should be scheduled, which are corresponding respectively to work-conserving and non-work-conserving algorithms. So we can record the order or time as the rank or priority of a flow, and implement a scheduling algorithm with multiple PIFO blocks. Each PIFO block is a physical priority queue that can be partitioned into multiple logical PIFOs, and the mesh of PIFO blocks can be configured into a multi-level scheduling tree. Within a PIFO block, a flow is pushed into an arbitrary position based on its rank and is popped when its rank is the smallest in the queue. Once the flow is popped, its first packet is scheduled, and if there are remaining packets, we will reinsert the flow back into the PIFO with a new rank. PIFO is initially designed for traffic manager in programmable switches, and it can also be utilized in SmartNICs, such as Loom in 2019 and Panic in 2020. The original priority queue implementation of PIFO is shift registers, which use a compare and write pipeline requiring 2 clock cycles for a push or pop operation. However, shift registers are not scalable. In a shift register with n elements, we need n registers to store the ranks, 2 times n comparators, and 2 n input priority encoders. As n increases, it will consume massive resources, and the frequency will drop sharply. There are 2 approaches to address this issue. The first one is to opt for an approximate PIFO rather than a strict PIFO. We can replace the priority queue with a group of FIFO queues, which has simpler implementation, less resource consumption, and higher frequency. For example, SP PIFO in 2020, IFO in 2021, and PAX in 2025. The second approach is to implement the priority queue with a novel structure, such as APQ, BMW tree, and BBQ. ClubHeap also falls in this category. Now let's revisit the roadmap of priority queues. We can evaluate a priority queue in 3 dimensions: throughput, resource consumption, and scalability. Regarding scalability, we also have 3 parameters: the number of elements, the number of priority levels, and the number of logical PIFOs. As discussed before, shift registers are not scalable for M. On the other hand, increasing P has minor influence because it only introduces a minor increase in gate delays within the comparators. Similarly, accommodating more logical PIFOs in a shift register also has minor influence. Another classic solution is a systolic array. By doubling the number of registers and pipelining the push or pop process, systolic arrays do not need priority encoders and can maintain a high frequency as n increases. In 1997, Mu et al. Embedded shift registers within a systolic array, and this SIMD design was refined by APQ in 2018, which is a state-of-the-art priority queue implementation for small-scale n values. However, the ON comparators still limit its scalability for M, and it does not support more than 1 logical PIFOs within a physical structure. As a linear structures, including shift registers and systolic arrays lack scalability for M, researchers tend to a different category of priority queue implementations, that is, bucket-based structures such as BBQ in 2024, which assigns a dedicated bucket to each priority level, and when popping an element, we scan for a non-empty bucket with the highest priority. It doesn't need any comparators, so it has very simple circuit and can achieve very high frequency. However, it lacks scalability for both P and M. An additional priority bit will double the number of buckets, and the double logical PIFOs will also double the number of packets. To achieve scalability across the 3 parameters, we turned to heap-based structures. Hardware heaps perform push and pop operations just like that in the software, and these operations can be pipelined like in a systolic array. One operation will only access one pair of sibling nodes at each level, so it requires only O log n gates, resulting in good scalability for M. The state-of-the-art heap design, BMW tree, does not support multiple logical PIFOs, but a previous design, pipeline heap, provides the technique of dynamic memory allocation to overcome this limitation. ClubHeap has both advantages of these 2 designs as the first priority queue to simultaneously achieve scalability across M, P, and M with a relatively high throughput. Now I will introduce how we design ClubHeap. The core insight is that frequency does not mean throughput. Here we consider 2 priority queues. PQ1 has a higher frequency but can perform push or pop every 2 cycles, while PQ2 can perform both operations every 1 cycle. We can easily get that the number of push and pop will balance out when there are sufficiently many operations due to the finite size of M. So PQ1 has twice frequency, but PQ2 has twice maximum sustainable throughput. Here we introduce a new metric, cycles per replace, where replace means pop and push. When CPR is a constant, the maximum sustainable throughput can be computed with the frequency divided by CPR. For example, BMW tree can issue 1 push and 1 pop within 3 clock cycles, so its CPR is 3. BBQ has a CPR of 2, and APQ has a CPR of 1. As a heap-based structure, ClubHeap has a similar frequency to BMW tree, but thanks to the SIMD technique borrowed from APQ, ClubHeap can also achieve a CPR of 1. So it has almost 3 times throughput than BMW tree. Why is SIMD so important? Let's discuss the inter-operational data dependency problem for existing heap-based structures. Consider back-to-back pop operations on a heap. In cycle 1, we pop the element 1, and in cycle 2, we should pop the element 2. However, the element 2 is on the 2nd level. We need to wait for a clock cycle for the first pop operation lifting the element 2 to the 1st level, or we need to add bypasses between the levels, which would form a crossbar interconnection resulting in poor scalability for M. To solve this problem, ClubHeap organizes K elements as a cluster in each node. It is defined by 2 features. First, elements in each cluster are sorted. Here we treat empty slots as infinity so that non-full clusters concentrate the elements toward the front. Second, any element in the parent cluster is not larger than any element in its children cluster. So the parent of a non-empty cluster must be a full cluster, and elements are concentrated toward the root. So the inter-cluster ordering can simplify local operations at each level, just like a shift register, providing high frequency. And the inter-cluster partial ordering can address the IODD problem in the same way as APQ, so that CPR is 1. And finally, we can get a high throughput. We can use an example to show how we solve IODD problem. In cycle 1, we pop the element 1, and in cycle 2, the element 2 is already at the 1st level because each cluster will contain at least 2 elements. When we pop the element 2 at the same time, the first pop operation will lift the element 4 to the 1st level, ensuring there are always valid elements to be popped at the 1st level. Another advantage comes from the element concentration. We focus on this question: how many non-empty nodes are there in the else level? Thanks to the concentration, we can get an upper bound B1, which is independent of M. And we can also get an upper bound B2 as the maximum number of nodes in M binary trees. In ClubHeap, we can choose the smaller one between B1 and B2 as the size of RAM at the else level. This method can save 70% of SRAM when M is 16. The cluster size is a tuning parameter which can balance performance and resource efficiency. Larger K values can increase the frequency, and smaller K values can save more resource. We suggest setting K between 2 and 16 for good balance. Another parameter is heap weightiness, but our experimental results show that clustered ternary heap or four-way heap consumes much more resources, but with no frequency improvement. So binary is optimal. Now let's compare ClubHeap with the state-of-the-art designs BMW tree and BBQ. First, we discuss different N values. With a CPR of 1, ClubHeap can achieve 3 times throughput than BMW tree with similar resource consumption. Although BBQ has almost twice the frequency, we have half the CPR, so we can achieve similar throughput to BBQ and only consume 1/4 BRAM, which is the primary FPGA resource required by these structures. Let's move to the scalability for P. When the bit width of P grows from 16 to 32, ClubHeap maintains its high throughput with only 5% reduction, while BBQ has poor scalability because of the exhausted BRAMs. For the same reason, BBQ is not scalable for the number of logical PIFOs, while BMW tree does not support logical partitioning at all. On the other hand, in ClubHeap, there is only 1/6 frequency reduction when M is 256 and K is 2. And when K is 16, there is almost no frequency reduction. To conclude, ClubHeap has high frequency and CPR of 1, and good scalability for N, P, and M. It can be embedded into PIFO schedulers in programmable switches or SmartNICs, or other schedulers requiring priority queues, such as PIFO and tussle. Finally, we discuss some limitations of ClubHeap. It does not support extended scheduling abstractions such as DR PIFO and PIEO, and is limited to on-chip SRAM memory. We also have found that our 3-stage pipeline is not optimal, so we have been working to improve the pipeline design to make ClubHeap operating in a higher frequency. Thank you very much, and any questions are welcome.